Hey everybody, it's Mr. Covey here, and this is in page 4 of your note packet. It looks like this. We've already done some intro opening problems together, so we're going to jump right into what we usually do as some stations, but we're going to kind of just like do them as notes in this video. It'll work out. So the idea here is there's going to be an algebraic equation and then a trig equation that kind of mirrors the format of the trig equation. Okay, it's kind of like when we first did the verifying identities thing. You're going to look at this algebra expression. We did with verifying identities, they were algebra expressions and trig identities, but here we're going to do it with algebraic equations and trig equations. So you're going to solve the algebra equation, and then you're going to solve the trig equation using the same strategy. Okay? I'll show you a couple examples, and you guys will get a hang of this. Cool? We're solving all of the equations on 0 to 2 pi, which means we're only giving out angles in radians and only angles between 0 and 2 pi, including 0, not including 2 pi. Please read this remember thing. Okay, this is algebra from pre-algebra, algebra 1 and algebra 2. We are reviewing it because we know you guys are shaky on it. It's tricky stuff. But you do need to know the algebra or you're not going to be able to do the trig equations because the trig equations are built on the algebra equations. Okay? So if you go to your page that looks, the next page in your note packet, what you'll see is a little label that says type/solving strategy. That's the algebra strategy, the algebra type of equation. Then we're going to solve an algebraic equation and a trig equation that's similar. I'm going to do some of these with you and let you guys try some, and we'll kind of bounce back and forth. So always look at the algebra first. Okay, so here's an algebraic equation. Linear equation. You guys know how to solve this. Get the x by itself. Add square root of 2 to both sides. 2x equals square root of 2. How do you get the x by itself? You divide both sides by 2. So linear equation. X equals square root of 2 over 2. You know how to solve linear algebraic equations. You can solve linear trig equations too. You follow the same steps. Everything's exactly the same. Nothing changes at all until the very end. You are not done at this point, but the only remaining step is something that I'm confident you guys can do. Tell me the angles whose sine is root 2 over 2. Theta is not root 2 over 2. Theta is an angle. Theta is not root 2 over 2. Theta is like some angles, pi, theta, sine, whatever. Tell me the angles that have a sine of root 2 over 2. Think about it. In the first quadrant, there's an answer, and there's an answer in the second quadrant. It's going to be pi fourths and 3 pi fourths. Okay. Normally, generally, not always, but generally, trig equations have 2 solutions between 0 and 2 pi. So I know the linear equation only had 1 solution, but because of how the unit circle works, when you ask yourself, like, well, how many times does sine equal that number? It usually happens twice. Not always, but generally there's 2 solutions to trig equations between 0 and 2 pi. Okay. Pause. Try and solve that algebraic equation. Note that the strategy here is GCF. Take a GCF. Check. Cool. Please don't do this. I'm gonna cry if somebody does this. Mrs. Lemke's gonna get mad. You guys ever seen Mrs. Lemke mad? Scared? Scared? Alright. Don't do this. Don't add the x over and divide both sides by x. I know somebody did this. You get x equals 1. What happens when you do that is that you miss a solution, okay? You might remember from your algebra classes, this is never something you do because you never divide by x when you're solving an equation. Never divide by x. That's just an algebra rule. It's one of those things like you can't divide by 0. You never divide by x when you're doing algebra. And similarly, when you do trig equations, you never divide by everything by sine. No, that's never something you do. All right, that's the algebra strategy. Let's do this same thing with trig here. So I'm going to factor out a sine of beta. That's a beta. Okay, you should know your Greek letters. We'll remind you of them, but you need to know them. Okay, factor out sine of beta. We're left with sine of beta minus 1 equals 0. Set each one equal to 0. Trying to figure out when sine of beta equals 0 and sine of beta minus 1 equals 0. So when sine of beta equals 1. Think about between 0 and 2 pi, when an angle has a sine of 0. Think about it. What happens when my angle is 0 and when my angle is pi. Think about when your angles have a sine of 1. That's only pi halves. This is one of the examples where you actually don't have two answers between 0 and 2 pi. Okay. Put it all together, though, this equation has 3 solutions. Okay, so you do have to be careful about the number of solutions, because the number of solutions to the algebra part and to the trig part aren't always the same. In fact, they're usually different. I'm just going to let you guys try to do this one on your own. Okay? Take a couple minutes, try to do it on your own. I'm going to go over it after. Should be trying this on your own. Okay, let's chat algebra. When I look at this equation, first of all, this is asking me just to do normal factoring. Hope you guys remember normal factoring. What multiplies to 1 adds to 2, 1 and 1. I end up getting x equals 1 and x equals 1, so my answer is just x equals negative 1, x equals negative 1, so my answer is just x equals negative 1. Notice that when I glanced at this, I said, oh, this is a quadratic equation. I expected there to be 2 solutions. Usually quadratics have 2 solutions, but sometimes they have 1. Okay, why did they have 1 here? Because both the factors were the same. I'm just drawing your attention to the number of solutions idea because it is something you need to be careful about. Okay, come to the trig equation. I'm going to do the same thing. If you want, we are no longer verifying identities, so the formatting of our work matters less. Still important, but it matters less. If you are uncomfortable trying to factor with these cosines and squares and cosines, I hope you're better at it. That's why we did the verifying identities unit first. It's kind of the reason that we do it in the order we do it. But you always can replace those with a variable. Just make sure you clearly define what you're replacing it with. Rewrite it like this. Factor this if it's easier for you to think about. And then after you've done the algebra, switch it back to cosine. You have to show this out though. And then answer the question. When does cosine equal negative 1? Or when your angle's pi? Okay. That's it. Okay. Let's keep going through this, cool? If you kind of think about it, like every algebra equation you can solve, we're going to solve trig versions of that too. So whatever your favorite algebra equation is, I know we all have our own favorite algebra equations. We're going to solve trig equations that look like that. You guys want to do this one together? Yeah. Okay. We'll do it together. So this is, I'm going to do factoring, but the leading coefficient is not 1. So first thing, I'm going to move it all over to the same side. And now I'm going to factor this. There's 2 ways to factor this. The strategy I just used there is called the big boy way. You guys can write that down if you want. It's called the big boy way. It is me just thinking about how factoring works and figuring out how it factors. This is what I did. Ready? I said I know that the first 2 things have to multiply to 2x squared, so I put a 2x and an x, because that's what's going to multiply to 2x squared. And when I was trying to think about these 2 numbers, I said they have to multiply to negative 1. And when I do inner and outer, they better combine to give me negative x. So 1 times x is x, negative 1 times 2x is negative 2x. Put those together, you get a negative x. That factoring strategy is called guess and check. Okay? You just kind of guess what the factors are until you figure out 2 that work. Alternatively, a lot of you guys use split the middle. Being the nice, generous math teacher I am, I'm going to review split the middle with you one time, and no more. This is something you need to know how to factor, okay? This is algebra 1, okay? A lot of you guys do this strategy. You do 2 times negative 2, excuse me, 2 times negative 1 to get negative 2. So you're looking for two numbers that multiply to negative 2. You have to multiply those two together to figure out what you're going to multiply to. So you're looking for two numbers that multiply to negative 2, and they have to add up to negative 1. Okay. Well, negative 2 and 1 multiply to negative 2 and add to negative 1. Once you figure out those two numbers, you have to split the middle. So you're still going to have the 2x squared. You're still going to have, let me move this way. You're still going to have the minus 1, but you're going to split that minus 1x into a negative 2x and a plus 1x. You split it. That's why it's called split the middle. Some of you guys call it curtains or something like that, or drapes. Can't remember. Once you do that, you group these together, and you group these together, and you take out a GCF. And then the GCF, or excuse me, what is left after the GCF should be the same for both of those, and that is one of your factors. And the GCFs you took out come together to form the other factor. The one thing to be careful about here is when you're saying, a lot of people say, well, multiplies to negative 1 and adds to negative 1. No, when you have a coefficient out here, you need to multiply this front number times this last number to figure out what your two numbers are supposed to multiply to. This technique of factoring is kind of long and drawn out, and I would not recommend it because you guys are big boys and girls. So just figure out how it factors. At the end of the day, though, it doesn't really matter. You just need to be able to factor. Then if you can't do the algebra, you can't do the trig equations. So now that you've factored, you set each factor equal to 0, and you get x equals 1. If you set 2x plus 1 equal to 0, you get x equals negative a half. That's the algebra version. Solve the trig version now. Go ahead, pause, give it a try. You can solve this trig version. It's going to look exactly the same. Just at the end, you're going to have to find the angles. Okay. So there was 2 cosine squared of alpha minus cosine of alpha equals 1. I moved it all over to the same side. I factored it. Again, if you want to switch the cosines of alphas to p's or something, so that you can make sure that you factor it right and do the split the middle thing, that's okay. That's totally fine. I want to make sure that you get it factored right. Set each individual factor equal to 0. I figured out my solutions are going to be where cosine equals negative 1/2 and cosine equals 1. When does cosine equal negative 1/2? 2 pi thirds and 4 pi thirds. When does cosine equal 1? At an angle equal to 0 radians. So I got 3 solutions to this. Okay. Again, I cannot emphasize enough the number of solutions to the algebra equation is not necessarily and usually not the same as the number of solutions to the trig equation. The trig equation generally has the same or more solutions. Okay. You guys do this one real quick. I'm going to fly through this one. Not bad at all. Radical equations are actually Mrs. Fry's favorite type of equation because she's a little radical. That's radical equations. All right, go ahead and solve these. We'll check over them in a minute. Okay. How do you solve radical equations? You get the radical by itself. You get the square root. Remember, radical is a fancy name for square roots. You get the square root by itself, and then you square both sides. So how do you cancel out a square root? By squaring both sides. You do not need a plus or minus for radical equations. I repeat, you do not need a plus or minus for radical equations. A plus or minus comes up when you square root both sides, not when you square both sides. Okay? There's no plus or minus. Same thing with the trig. Do. When does cosine equal 1? When theta equals 0. Let's move forward. Difference of 2 squares. An oldie but a goodie. Go ahead, give it a try. We'll chat together. Make sure you can do this algebra. Okie dokie. Difference of two squares. 2x plus 1, 2x minus 1. Set it equal to 0, you get x equals negative 1/2 and x equals 1/2. Very similar structure here. 2 sine x minus 1 times 2 sine x plus 1. Sine x equals 1/2 and negative 1/2. Sine equals 1/2 at pi 6, 5 pi 6. Sine equals negative 1/2 at 7 pi 6, 11 pi 6. Notice we got 4 solutions to this single trig equation. Okay. Please be on the lookout for making sure that you get all of your solutions. 2 comments. If you do not know this algebra, go in for help immediately. I repeat, if this algebra is looking like you don't understand it, go in for help immediately. We are not reviewing this algebra anymore in this class. Okay, we are expecting that you know how to do factoring. Okay. Second comment. You also could have solved this equation how? Well, you could have used square roots. You could have added the 1 over divided both sides by 4, put it in the square root of both sides, added a plus or minus, you would have gotten the same solution. So if you wanted to use square roots to solve this equation, that would have been totally fine as well. Okay. We got one more challenge, and then we're out of here. Okay. Pause. Give this one a try. I'm telling you the algebraic strategy is grouping. Good old-fashioned group. Give it a try. Try it with the trig functions. We'll chat. Okay. So here, grouping. You guys know how to do grouping. Take the first 2, take out a GCF, see what you're left with. Group the second 2, take out a GCF. Note that if that term right there, that first term in the second group is negative, you should take out a negative GCF. That's kind of just how it works out. You'll notice that what you're left with after you take the GCF out of the first group and the second group is the same. That becomes one of the factors. The GCFs themselves become the other factor. Hope this is all looking really familiar. We've been doing this too. Solve it, you get 1 and negative 1. With the trig stuff, same thing. Everything's exactly the same. When does sine equal 1 or negative 1? Well, it equals 1 at pi halves and negative 1 at 3 pi halves. Okay. We are not going to spend a lot of time in this class practicing stuff like this. We'll spend some time, but it's kind of expected that you can kind of do this. There's no real new skills in this. There's factoring, which we've been doing for the last month when we've been verifying identities, factoring trig stuff, and then figuring out when trig stuff equals certain values, which we've been doing for the last 3 months. Cool. So we're just putting together 2 skills that we expect you guys to be able to do. Our focus is going to be on something that is a little bit trickier. Take a look at this challenge question here. Cosine squared minus sine squared equals 0. What's different about this equation? Well, it's got 2 different trig functions. That's completely different than like any of the other ones. Like it may be complicated, but they're all cosines or they're all sines. This equation has a cosine and a sine. Okay. So if you think about it that way, it's definitely harder. But if you frame it in that light, the strategy becomes kind of clear. You look at it and you go, wait a second. I don't want 2 different trig functions. I want either all to be sines or all to be cosines. Let's make it all into sines. How would I switch my cosine squared into sines? Well, I'd replace it using a Pythagorean identity, good old-fashioned Pythagorean identity. I'd replace that cosine squared with a 1 minus sine squared. And now look. This looks much more like the equations we've been solving. Okay, I'm not even going to finish that one up. I'm just going to note that the next strategy we're going to learn next class is going to involve using Pythagorean identities to help us get trig equations that look like this into trig equations that look like this, because this looks like the ones we just solved, and I'm confident you guys can solve this. well, this looks weird. It's all going to be about the Pythagorean identities, but that's for next class. For now, I hope all the problems before this last challenge one were smooth. Cool, because we do expect you to be able to do those. And if not, do some practice. Come in for help. That concludes this video. Thanks for watching.